Hello, everybody. So the second part of this section talks about the uniform field when we have a uniform field, and the net force is zero, of course, because we write it down. We're gonna have the force equals to the current times the closed integral of dl cross b is equals to, well, it's equals to current and then the closed integral of dl, which we already know what it is, cross b, and it's equals to zero. This one comes out of the integral because it's constant. You just said it's a uniform field, and um, and since this is a closed loop, this ends up being zero. All right. So now, what happens when we have a non-uniform field? Well, it's a little complicated to measure a non-uniform field, but this is given usually by a coil. So let's imagine we have a let me just draw it better. A cylinder with a wire around it. Um, so I'm going to make a wire like this. The current going in this direction. Um, oh, yeah, it's fine. We don't really need to. Anyway, we have magnetic field going outside in this direction. I would almost say in a radial direction. And on top, we have a current loop with current moving along it. So now we have to find the force. Now, in this case, we have to use the right-hand rule with the palm. So we take our palm and we point it, we take our hand and we point it with all four closed fingers, we point it towards where the current is moving. So, for example, if we take the right side, we're going to point it towards us. Then the palm is going to point towards the direction of the magnetic field, which is up. And we have our thumb that points in down direction. And this means that the force will actually be pushing down. And this force can be calculated by saying that it's equals to 2 pi I, actually I'm going to write it the way I like to write it, R I B cosine of theta. As you can see, this 2 pi R is equals to the circumference of our loop, because we know it's a closed loop. And the force will actually push in a different direction based on where we are, because the left pushes towards the left and down, on the right pushes towards the uh, right and down. And instead, for a infinitesimal loop, we can rewrite this as the divergence of the magnetic moment, dot the field. Now, as you can see, the magnetic moment, as we established in the previous video already, it's equals to IAB in the square that we did before. So if we look back at the square that we had before, AB was the area that we had before, and I was the current that was going through it. Okay, and this takes care of our initial part. Let me do another color so it's more easy. Okay, and the cosine part comes from this dot. It's just a dot product, therefore it's going to be cosine of theta. Cosine of the vectors. Cosine of the angle between the two vectors. And that is pretty much how you solve this. The problem is not too difficult. The book then goes and explains that initially physicists thought of magnetic dipoles as electric dipoles. So, for example, they call the south pole and the north pole, as well as the negative pole and not positive pole, which is incorrect. Now, it works well with some numbers, with numbers, but it actually is incorrect because it is wrong on Tegel cycles. For example, if we were to break this down in half, we would have two magnets, north and south pole, and north and south pole. Well, if we break this down in two parts, we would have a positive side, and a more negative side. That's that's the reason why it doesn't work. So the best way of thinking about it is through the concept that we have a magnetic moment when we have moving current. So we have something like this, right? And this one that we have on the right, that is the right way, is called Unpairs Model. And the one on the left instead is called Gilbert's. Actually, no, this one. Gilbert's model. And now, so far, we've seen that these things are actually, I mean, the initial assumption that these two are the same is pretty justifiable based on what we saw so far. However, it does not hold on based on future things that we'll see.